Welcome to Lecture 4, Earth's Orbit and Its Effects. As I've mentioned a couple of times, and as you probably knew when you registered for this course, the title of the course is Stars in the Universe. So we won't be spending a lot of time inside the solar system and focusing on the Earth and the other planets. Having said that, one of the other messages that I want to reiterate is that everything we know about the universe, both inside and outside the solar system, essentially comes from the light that we receive here on Earth. And so, as it turns out, it's actually relatively important to understand at least the Earth's orbit because it makes a big difference in terms of how we observe the universe, what parts of the sky we can see, when we can see it, seasons, and the like. So today we're going to focus on the Earth, on its orbit, and what effects that orbit has on the observations we make. As you probably know, the Earth orbits the Sun. And as I just claimed, this fact alone is significant enough that it impacts what we observe, not only in our immediate environment in the solar system, but also the appearance of relatively near or local stars. And actually, as it turns out, we can exploit this fact to actually learn things about stars. And in particular, we'll talk in a little bit about how the use of parallax allows us to use our orbit to measure the distances to nearby stars. But another important aspect that we're going to focus on more immediately is the tilt of the Earth. And in particular, the fact that the Earth's axis is tilted at an angle of 23.5 degrees relative to the plane of the solar system. Or to put it another way, if you draw a line from the Sun to the Earth's axis, which you can see if faintly here, is tilted 23.5 degrees relative to the perpendicular. So again, if you draw a line connecting the Sun and the Earth, then draw a line perpendicular to that line, the Earth's axis is 23.5 degrees rotated relative to that line. And it turns out that's going to make a big difference. So if I'm going to play this animation here, which is it's a short one, 30 seconds, but it does a good job, I think, of showing that this angle of rotation is consistent regardless of where the Earth is in its orbit. So as the year passes, the Earth orbits around the Sun, but the angle, this 23.5 degree tilt of the Earth's axis relative to the solar system plane is consistent. And so that's going to have a very important effect on the intensity and the directness of the light from the Sun as it impacts the Earth. So the Earth takes a year to orbit the Sun, and that's not a very profound statement because that's the definition of a year. Okay, that's what an Earth year is, and that just because we're Earth-bound. When we refer to years, we mean Earth years. So when we talk about, Jupiter's orbit, for example, we say Jupiter's orbit is so many years, we mean Earth years. Naturally, if we wanted to use Jupiter units, we could say that Jupiter's year is 1 Jupiter year. But we don't. We stick with Earth units. So a couple of other things that you probably already know, but it's worth putting on a slide for completeness. The Earth, in addition to its orbit, the Earth spins around its axis. And it does that in 24 hours. That's the definition of a day. Now, it turns out that the orbit of the Earth, we typically say 365 days, right? But it's actually very, very close to 365 days and 6 hours, or 365.25 days. And this is the reason for having a leap day every 4 years. So a leap year is a year in which we say, well, we kind of shortchanged 3 years in a row where we said there were 365 days instead of 365.25 days. And so every 4th year we say, okay, we're going to take all of those 3 times 6 hours that we missed in the prior 3 years, and then the 6 hours extra for this year, we're going to lump them together into one more 24-hour day, and we add a leap day to the end of February. Now, how do we interpret the shadow? And by that, All I mean is that as the sun, wherever the Earth is in the sun's orbit, obviously part of the Earth is illuminated, and that's the part that's having daytime, and part of the Earth is darkened, and that's the part that's at night. And obviously that changes as a result of the Earth's rotation. So let's take a look at this schematic and just think for a second, or maybe 30 seconds here, which of these people has a time of 6 a.m. currently? And one thing, in order to answer this, one thing you certainly need to know is that the Earth rotates counterclockwise as viewed from above the North Pole. And so, in other words, if I am located if I'm located up here and I'm looking down, the Earth is rotating counterclockwise. And so this guy is rotating towards the sun right now. This guy is rotating away from the sun right now, and and so on. So I'll give you 30 seconds. Think about this for a little bit and try to answer for which person is the time 6 a.m. Okay, so let's come back then. 6 a.m. is roughly sunrise, right? Obviously, sunrise changes a little bit over the course of the year, but 6 a.m. is roughly sunrise. And so when we think about 6 a.m., what that means for analyzing a diagram like this is that wherever the guy is, he needs to be rotating towards the sun in such a way that he is just starting to be able to see it. Okay, so let's go through and see what these guys look like. So if you look at A, he doesn't see any of the sun, right? He is as far away from the sun, from being able to view the sun as possible. He's on the other side of the Earth. So this guy, if you had to pick a time, this guy's at midnight. He's in the middle, literally the middle of the night. He's rotated away from the sun as much as possible, and he's definitely not seeing it. So this guy's around midnight. He's not anywhere close to seeing the sun. This guy, let's go ahead and jump over to C. Well, C is high noon, if you will. The sun is directly overhead for him. Despite the fact that he's drawn in black, he is as illuminated as possible, and you can see that. He's on the side of the Earth that's fully illuminated here, and so he's at noon. Okay, so that's definitely not 6 a.m. either. So now the question is, well, which one of these guys, B or D, do we think is going to be 6 a.m.? And here, the answer depends critically on the direction of rotation of the Earth again. So if you remember, again, the Earth rotates counterclockwise as viewed from above, so as viewed from up here, say. And so this guy B is rotating towards the sun, whereas the guy in D is rotating away from the sun. So this is essentially sunrise. He is just, if you imagine a little bit earlier in the day, he would have been a little bit almost behind the Earth here, hidden. So he is just rotating out, into a position where he can see the sun. Whereas down in D, this guy is rotating just away from the sun, and so the sun is just starting to disappear. And so B is essentially sunrise, and D is essentially sunset. And so the answer then for 6 a.m. will be B. Now, because the Earth orbits the sun, different constellations are visible at night at different times of the year. Essentially, where we are in the orbit determines what part of the sky we see at night. Obviously, all the stars are always there, but during the daytime, the sun is so bright that it washes out everything else in the sky. We don't see anything. So we only see the stars at night we only see stars at night unless, of course, there's a solar eclipse. And so what stars we'll be able to see depends upon the time of the year. So, for example, on September 1st, the sun is seen in the direction of Leo as viewed from the Earth. Another term that we haven't talked about yet, but we'll use periodically, is that the apparent path the sun follows against the background of the stars is known as the ecliptic. So that's just, we won't use it a lot because, again, we tend to be focused on, in this class, outside the solar system and not on the sun itself particularly, but essentially occasionally we will use the term ecliptic. And then by December 1st, Earth has traveled far enough. So this is September. Again, we're in Leo. In December, it's 3 months later. So we've traveled a quarter of the distance around the sun, essentially, and we've traveled far enough that the sun is seen in the direction of Scorpius. And so, I don't know anything about the zodiac, but for those of you that may, these are the signs of the zodiac, and they correlate with months of the year. But as you may or may not know, the constellations aren't the only thing that changes through the year as we orbit around the sun. And in particular, one of the most notable things, you don't need to know anything about the zodiac to recognize that the seasons change. And so what I want to focus on now for a few minutes is what factors do you think that might affect seasons on the Earth? So here are 4 possibilities. And I'll pause. You can read perfectly well yourself, so I'll pause here for 30 seconds or so and give you a chance to read through these options. But the question is, why does the Earth experience seasons? Okay, so now that you've had a chance to read through the options, let's go ahead and go through them one by one. So we're going to go through all of these 4 possibilities one by one, but in the spirit of focusing on the right answer before we focus on the wrong answers. The correct answer is D. The reason that the Earth experiences seasons is that the tilt of the Earth's axis causes there to be more direct sunlight incident on the Earth during summer than in winter. And of course, when summer and winter are depends upon where you are in the Earth, right? And we'll talk about this in a little more detail in the next couple of slides. But obviously when it's summer in the northern hemisphere, it's winter in the southern hemisphere and vice versa. So let's dig into this a little bit further. So this is not a scale drawing, as you can imagine, but it does illustrate the key impact here, which is that because the Earth's axis is tilted relative to the plane of the solar system, the sunlight is more direct on part of the sun than it is on others. And so as you see in this particular schematic, the southern hemisphere is tilted towards the sun, and so it is receiving more direct sunlight, while the northern hemisphere is tilted away from the sun, receiving less direct sunlight. And then as a result, this is summer in the southern hemisphere and winter in the northern hemisphere. Here on this slide, we've zoomed in a little bit more, and so it's obviously still very much not to scale, but it does give a clear indication of why the directness or indirectness of the sun's rays makes such a big difference in terms of what we experience here on Earth. And in particular, if you follow these 3 rays of light that have been identified, kind of, coming from a couple of different parts of the sun, in the southern hemisphere, which is receiving the more direct sunlight, those 3 rays of light are concentrated in a relatively small area. And so if you think about each ray as carrying along a certain amount of energy, that means that all of that energy is deposited in a relatively small area on Earth. And as you might expect, when you deposit more energy in a small area, things get hotter. In contrast, because the northern hemisphere is tilted away from the Earth, those same 3 sun rays, if you will, get spread out over a larger surface area of the Earth. And so the same amount of energy is spread out across a larger area. That means that each square centimeter or square meter, if you will, of the Earth's surface is getting less energy, and so it's going to be colder. And so this is the reason, in one slide, this is the reason why seasons exist. This is why it's hotter in summer and colder in winter. And this is why, as a matter of fact, things don't change much at all very near the equator, because if you're very near the equator, whether you're tilted towards or away really doesn't matter, because you're getting very direct sunlight in either case. So that's the right answer. I like, when at all possible, I like to focus on the right answer first, because there are all sorts of arguments that you can make that would be compelling for wrong answers, but we don't want to get confused. So the reason that seasons exist is the tilt of the Earth's axis and the implications that that has on how direct or indirect the sunlight is that strikes the Earth. Let's take a look at the other answers, though, and see if we can understand why these are not correct, and what difference they make, if any. So let's focus first on answer C, the tilt of the Earth's axis. Okay, so we have identified the tilt of the Earth's axis as part of the correct answer, but the focus of answer C here was the claim that it causes there to be longer hours of daylight in the summer than in the winter. And it's true that there are longer days in the summer than in the winter, in the sense that, if you look at when sunrise is and when sunset is, the difference, between those, the duration during which the sun is visible in the sky, is longer in the summer than in the winter. But that doesn't really impact the weather particularly, certainly not nearly as much as the directness of the sun. So if you're interested in a few specific points, one interesting note that you may already know, but is that from the Arctic Circle to the North Pole during the summer, there are 24 hours of daylight. And so this defines the Arctic Circle. The Arctic Circle is the area, or is the region around the North Pole that never sees a sunset during summer. And it's pretty wild to think about that, but certainly this is, and people don't see it in person a lot, because not very many people live at the North Pole, but there are certainly people that live near the North Pole, even in Scandinavian countries like Norway or Sweden. These are, very far north. And so, there are times where the sun will rise at, say, 4 a.m. and set at 11 p.m. or something like that, where you get a whole lot more sunlight in the summer than maybe the 12 or 13 or 14 hours that you might, consider normal. The flip side is also true, though. It means that in winter, you're barely seeing the sun at all. The sun might rise at 10 o'clock in the morning and set at 2 or 3 in the afternoon. I remember when I was in college in Boston, I remember walking back from classes sometimes at 3:30 in the afternoon, and the sun was getting ready to set. And I remember thinking, this isn't right at all. And maybe that's why, people study so hard in New England, because, what else is there to do? But so this is definitely a thing. The days are definitely longer in the summer than in the winter, and how much longer they are is dependent upon how far north you are, or how far south you are. The same is true near the South Pole. So this is definitely impactful. If you like daylight throughout the year, then you would not want to live in Norway or Sweden, for example, or at the southern tip of Argentina. But this is not, what's responsible for seasons as we experience it. So let's look at another answer here. So the claim in answer A is the Earth is closer to the sun in summer and farther from the sun in winter. Now, this is a tempting answer, I think. I hope you weren't tempted too badly, since it's wrong. But you should pause for a second, and maybe more, because certainly we know that summer in the northern hemisphere is different than summer in the southern hemisphere, right? And so as a result, this answer couldn't possibly be true, because whenever it's summer in one part of the Earth, in one hemisphere, it is winter in the other, and vice versa. And as a matter of fact, the sun is actually farther away from the sun during the northern hemisphere's summer. So for us who live in the northern hemisphere, the sun is actually a little bit farther away from the sun during the summer than in the winter. But as a matter of fact, and we'll talk about this more in another week or so, the Earth's orbit is elliptical, so it's not perfectly circular, but it is so nearly circular that this effect is quite small. And yeah, so certainly not. It is neither true nor important for the Earth as far as its seasons go. Okay, so let's look at a few days, a few specific days that are kind of important that you may have heard referenced, and I want to make some connections to the Earth's orbit. So, and those are equinoxes and solstices. So there are equinoxes during the fall and the spring, and there are solstices during the summer and the winter. And basically, it just means that the Earth is, a quarter of the way around its orbit. So we start off, at the vernal equinox, which is a fancy name for the first day of spring, typically around March 21st, but sometimes it can be late on the day in the 20th. Sometimes it may be able to sneak into the wee hours in the morning on the 22nd. Every time that it comes around, there's some news report about it, and so you can always Google and find out exactly what day and hour, minute, second, and millisecond, and so on that the vernal equinox actually occurs on. But on that day, we have equal length days and nights, and so so the day and the night are exactly 12 hours on the vernal equinox. And similarly, on the autumnal equinox, it's the first day of fall, September 21st, usually, plus or minus a few hours that may carry you into the 20th or the 22nd. But again, you have equal length days and nights. And so, and then in contrast, kind of the other two quarter points are the solstices. And so the winter solstice is around December 21st, is the first day of winter. And then the summer solstice, and that's the shortest day of the year. The winter solstice, the shortest day of the year. And then on the flip side, the summer solstice is the first day of summer, very nearly June 21st, and it's the longest day of the year. So these are just, they're terms, they're definitions, and it's just, good to be aware of them. Okay, so now that you're experts on seasons and so on, I'm going to give you 30 seconds or so to ponder this slide. The question is just which one of these answers correctly labels the relative location of the Earth and the Sun and correlates them with the seasons. So I'll pause here and give you some time to think. Okay, so I think the starting point for analyzing this question, I think is to start off with summer and winter, because again, we know that the defining attribute of the seasons is, and summer and winter in particular, is how direct is the sunlight on the Earth. And so if you look, we're in the northern hemisphere. That's what we're asking about here, right? Because if we were asking about the southern hemisphere, everything would be flipped. So we need to know that. But in the northern hemisphere, we know that in summer the northern hemisphere will be tilted towards the sun. So we need to be. So let's look at summers. If we look at summer here, the northern hemisphere is tilted towards the sun, and so this is indeed summer. Okay, and in contrast, on the other side of the orbit, in winter, the northern hemisphere is tilted away from the sun. So summer and winter are correct here. In answer A. The only other question then is, what about fall and spring? Did we get those in the right order here? And fortunately, we can see we're orbiting counterclockwise about the sun as viewed from above. And so what comes after summer? Indeed, it is fall. Okay, so I don't know if it's good or bad that answer A looks like it's very reasonable, but let's go ahead and look through the others and see if they look right too, or if we can find out what's wrong there. So in answer B, you can see that we've got summer and winter flipped, and so that's wrong right off the bat. So we've got winter labeled with this location where the sun is, or where the northern hemisphere is tilted towards the sun. So that's certainly wrong. And then if you look at C and D, we can throw those out immediately as well, because they've got spring and fall, or fall and spring, labeled in those locations where the Earth is tilted, the northern hemisphere is tilted either towards or away from the sun. And so we know that those are going to be summer and winter for the reasons that we argued, and so the answer is A. So just to kind of bring it all together again, the winter solstice is the shortest day of the year, and that's where the northern hemisphere is tilted completely away from the sun, as you see in this diagram. The vernal equinox kind of comes next, in the sense that it comes 3 months later, when you have equal duration days and nights. You then have the summer solstice, which is the longest day of the year. It's the first day of summer. And then finally you have the autumnal equinox, where again you have equal length days and nights, and it's the first day of fall. So now that we're experts on the Earth's orbit and how that impacts us in a couple of ways, and particularly with regard to seasons, let's stop and think a little bit about the phases of the moon, which not surprisingly are going to have something to do with the moon's orbit. So fortunately, the moon is very easy to see. You don't need a telescope. If you have a telescope, it looks great. In fact, if you have a backyard telescope, the moon is by far the best thing to look at, because it is big enough that you can make a big difference. You can really see some features really well, and you can even take some pretty cool pictures with it, or of it. But the phases of the moon are nice to think about, because they're easy to relate to, in the sense that we see them every day if you pay any attention. And I have to say, since I started teaching astronomy, I find myself paying a lot more attention to the phases of the moon. And here are all of them. And in fact, there are even more pictures here than actual phases that we identify. But we're going to dig into this a little bit and try to understand what gives rise to the moon's phases, and what are they. So at the highest level, the reason that the moon experiences phases, of course, the moon doesn't actually experience phases. We experience the moon's phases when we look up at it. Is because of the relative position of the moon with respect to both the sun and the Earth. Okay, and this diagram here, again, very much not to scale, really I think summarizes it all. We're going to dig into it more, but the point is that the sun is always shining. Okay, it's shining during the day and it's shining during the night. Right. The only difference is that during daylight, we are on the side of the Earth that is facing the sun. Whereas at night, the Earth is rotated in such a way that we are on the opposite side of the Earth, where the sun can't get to us. So, and the same thing is true of the moon. Okay, so if we look at the moon, whatever part of the moon is facing the sun is illuminated. It's lit up. Okay, and so if we focus on the moon at this location, for example, there's always going to be a time during the month when the moon is in this location. Well, the sun is shining as always. The half of the moon that's facing the sun is lit up, okay? And then it's going to reflect that light back off into space. Okay, that's what it does. The moon, it's not a star, so it's not generating its own light, right? The only reason that it looks bright is that it's reflecting the sun's light. And what you'll notice about the moon as it goes, as it orbits, these are kind of snapshots of different times during a month as the moon orbits. Wherever the moon is in its orbit, it's lit up on the sun side. right? The sun side of the moon is lit up. But if we continue to think about the sun in this location, what are we going to see from Earth? Okay, well, we're not going to see anything because the side of the Earth that's facing us is dark, right? All of the light is on the sun side because that's the side that's getting illuminated. Okay, no light is getting to the back side of the moon here because it's being blocked by the front side of the moon. And so on Earth, we see a dark moon, okay, which is known as a new moon phase. And it means that you basically can't see the moon. If you squint hard, you can actually see it. It's not like perfectly dark, but it's very dark, right? So whereas in contrast, if we go to the flip side, say 2 weeks later, where the moon is on the back side of the Earth, now the sun's light is illuminating the moon on this side, same side, right? Still illuminating the left side or the sun-facing side of the moon. The catch here is, the big difference, is that now the moon is on the other side of the Earth, and so it's reflecting that light back towards the Earth. And so we now see a full moon. Okay, now, you should pause for a second here, because I hope that at least some of what I've said made sense. But there's a very good reason that you might pause and think, well, something doesn't make sense here. Because if you just look at this picture, at this slide as it is, it sure looks like the Earth is in between the sun and the moon. And so you could very legitimately ask, well, how on earth is that light getting to the moon at all? Isn't the Earth blocking it? Isn't this a lunar eclipse? Is what you're thinking. And the answer is no. And the reason is that this image is a two-dimensional image. But very importantly, the moon does not actually orbit in exactly the same plane as the Earth orbits the sun. Okay, this is difficult to show in 2 dimensions, and so I apologize for that. But essentially, you've got, if you imagine the sun is at my elbow and the Earth is out here at my fingertip, the moon it orbits the Earth above and below. It goes in a plane that's a little bit angled with respect to the angle of the plane of the solar system. And so as a result, the moon can be out here on the far side of the Earth from the sun, but it'll be, in general, it will typically be a little bit above or a little bit below the Earth, and so the sun's light will be able to get to it. Okay, if the moon was exactly in the same, orbited in exactly the same plane as the Earth did, then we would get a lunar eclipse every month. Okay, but we don't for exactly this reason, because the moon's orbit is at an incline. It orbits in a plane that is inclined at a relatively small angle, around 4 degrees, relative to the plane of the solar system. And that's critically important here. And so we get a new moon here, okay, where none of the reflected light gets to the Earth. We get a full moon here when all of the reflected light gets back towards Earth. And then in between, we get different amounts of reflection, right? So the important thing here is that half the moon is always illuminated. That half is always reflecting light back off into space. But only a fraction of that light is going to be sent towards Earth and be visible from Earth. And so we get none of it here. We get all of it here. Here and here, we get half of it. And then in between, we'll get slivers of it. And that's what gives rise to the phases of the moon. So back here in the full moon phase, this is what you see. If we're looking up at the moon, we see a full moon, thus the name, right? A few days later, you start to get part of the moon darkened, right? It always darkens from right to left, and it gets brighter from right to left as we view it. So this is called a waning gibbous phase. Waning because it's getting the amount of illumination of the moon is getting smaller as viewed from Earth. Then we get into what's called a third quarter phase, where the left half of the moon is illuminated. Then we get a waning crescent, which again, as I've said before, and I'll say again, fortunately, scientists, and at least specifically physicists and astronomers, are typically not very creative in their naming schemes. So it's waning, just means it's getting less bright, and it's a crescent because, look, it's a crescent. And then finally, the new moon, you can see it's sketched out very nicely there. It's just not there. You don't see it. And then as the moon continues to orbit, you start to recover some sight, right? You get to see it again. And so we get what's called a waxing crescent phase there. A first quarter phase that's blocked by my image here, and I apologize for that. But you can take a look at the slides without me here, and you can see that. And then there's again blocked by me in the lower right hand corner here is a waxing gibbous phase that leads you into the full moon. And those are all the phases. So I told you the first a couple slides ago there was a nice picture of lots of stages of development of the moon. These are the 8 phases that we really focus on that have names. Okay, and this is just to kind of summarize all of that again. And this is a nice summary. If you find yourself studying for a quiz or something, and on the moon's phases, which, as it turns out, is going to happen. At least it won't be entirely on moon phases, but it could be touched. This is a nice slide to review. Just kind of has all of the terminology, has all of the phases written in there, and kind of has all of the important features. And so one other thing that you can do is you can think about, if you're standing here on the moon or on the Earth looking at the moon, it turns out that there's a pretty cool connection between the phase of the moon and when the moon rises and sets. Okay, because when you think about, a moon rising or setting, obviously it looks like it rises and it looks like it sets from our vantage point, but really what's happening is that the Earth is rotating, right? And so here, fortunately, we've got the direction of rotation written here. And so, if you're standing here, this is sunrise. And how do you know? Well, you've just gotten to the point where you're able to see the sun for the first time. This is, if you look, the left side of the Earth is illuminated, the right side of the Earth is dark, and now you've just rotated from the darkness into the light. You can now just see the sun, and so the sun has just risen. So this is, if you're going to round, this is about 6 in the morning. Okay. Whereas this is noon. This is about 6 in the evening, about sunset. And I say about because, as I mentioned a few slides ago, the precise times for sunrise and sunset depend upon your latitude. They depend upon the season, where in the Earth's orbit you are, what time of year it is. And so, but, for the purposes of rounding and simplicity, we will, typically think about sunrise occurring around 6 a.m., sunset occurring about 6 p.m. So this is about 6 p.m. and then this is midnight. So, I said there's this connection. Let's think about it for a little bit. What time of day does a waning crescent moon rise? Okay, so that means you're in a waning crescent phase. So you can go back. I won't go back now because it kind of wreaks havoc on the video if I do that. But you can certainly pause me, and or bring up the PowerPoint slides themselves and go back and look at that slide a couple of slides back where you had all the phases of the moon sketched out and where the moon is relative to the Earth and the sun when it's in the waning crescent phase. And then think, okay, what time would a waning crescent moon rise? And so I'll pause for 30 seconds and let you consider. Okay, so to answer the question, it helps to start with this image, which is the one that I was alluding to about 30 seconds ago. So first, let's identify which one of these phases is the waning crescent. So we know that this is the new moon, right? Because again, we're standing here on Earth, And if all of the reflected light from the moon is going back towards the sun, none of it's coming towards Earth. So this is a new moon. A waning crescent is the phase right before the new moon. So it's going to be this one right here. Okay, so the question is, when do you see a moonrise from, when it's in this phase? So let's think about us as the Earth rotates. So back here, if we're standing here, at this point on the Earth, this would be midnight right now, because we're on the exact opposite side of the Earth from the sun, completely blocked by the Earth from the sun's light. Okay, whereas we've said right here is sunrise, right? And you can tell that because when you get around to this point, you're going from the darkness to the light. The Earth is rotating counterclockwise, remember. And so when you rotate up, you start here at midnight. This is about 3 a.m. This is 6 a.m. That's about sunrise. And then, if you kept going, this would be 9 a.m. This would be, and then 12 noon. Okay. So the question is, where in this development, somewhere between midnight and noon, obviously, do you first see the waning crescent moon? And you know that you see it before 6 a.m. because at 6 a.m. you start to be able to see the sun, and the sun is at a little bit. You have to rotate further before you see the sun, because you can see the moon is still rotated a little bit to the sort of in the clockwise direction here. So you're first able to see the moon when the moon's when the reflected light. So you see this light leaves the sun, part of it strikes the bottom of the moon here, which gets reflected back over here, and you start to be able to see it right about here, right when you've rotated halfway between midnight and sunrise at 6 a.m. And so it's right around 3 a.m. that a waning crescent moon rises. Now again, this is we're rounding to the nearest hour or so, because again the details will change depending upon where you are on the Earth, latitude in particular. But it's to a close approximation, a waning crescent rises at 3 a.m. And now you know why. And that's kind of all of the things that I just said. So you can obviously go back, get a hold of the slides and go back and review that. But it also might help. I find you may not want to do this. I find when I take out the trash, at night before trash day and things like that, or if I just step outside to, for whatever reason, I find myself often, checking to see, what phase the moon is in, and then thinking back to myself, okay, what time would that have risen or set? Or if I go outside and I don't see the moon, then I think, well, okay, is it that because it's a new moon phase, or is it because the moon just hasn't risen yet, or has already set based upon, the phase that it is and the time that I'm trying to observe it. So if you have trouble sleeping, you can always do that. Okay. One other important aspect of the moon's orbit is a property that's known as synchronous rotation. And again, it's what my high school chemistry teacher called the name thing, where the name actually says what it means. Okay. And so in particular, what it means is the moon takes exactly the same amount of time to orbit the Earth, so to make a complete circle around the Earth. It's actually an ellipse, but it's very nearly circle. So, but it takes exactly the same time to orbit as it does to spin on its axis. Okay. So another way of saying this is that if you were a moon creature, if you lived on the moon, your day and your year would be exactly the same length. Okay. That would be weird in the sense that it's very different from our experience. But that's how life is on the moon. And one of the corollaries for that, or one of the results, is that the same side of the moon always faces the Earth. Okay, because if you think about it, it kind of makes sense. If you're standing on the moon, facing, sort of facing the Earth, you're on the Earth side of the moon. Well, you're going to orbit and rotate at exactly the same angular rate. And so the result is that you're always going to be facing the Earth. Okay. And this is what gives rise to the concept, or to the term that you may have heard, the dark side of the moon. Okay. As we saw, or we didn't focus on it, but if you think back a few slides ago, what were those sketches of the moon kind of orbiting the Earth, you know, there's always half of the moon that's lit up, that's illuminated. That's the side facing the sun. And as you can see from this image, if you imagine the sun being off, you know, stage left, if you will, you know, the actual physical part of the moon that's illuminated is certainly changing. So there is no part of the moon that never sees the sun's light. Okay, so in that sense, there's no such thing as a dark side of the moon. Okay, it's not like half the side is half, you know, of the moon is always lit up, and that if you were sitting on that part, you would always be lit, and that there's another part of the moon that's always dark, that never sees the sun. That's not true. Okay, what is true is that there's a part of the moon that is always facing Earth, and there's a part of the moon that is never facing Earth. Okay, so it's a misnomer really to call it the dark side of the moon, you know, Transformers notwithstanding, but there is a part of the moon that always sees the Earth, and there's a part that never sees the Earth. And so it's better to call it the far side of the moon, because from Earth's vantage point, that is a thing. There is, you know, there's half of the moon that's always on the other side that we never see from Earth. It would be different if the moon didn't rotate, right? If the moon didn't rotate about its axis, if it just orbited, but, you know, just orbited as a big sphere, without any sort of axial rotation, then it would be different. Then sometimes you would be, you know, if you were standing on the moon, sometimes you would be facing the Earth, and then as you orbited, you would orbit, you know, such that you were then facing away from the Earth, and then you would come back around. Okay, so this would be the case if you had no rotation. Okay, but that's not what we have. What the moon actually does is it undergoes, again, synchronous rotation, which, again, name thing, just means that it orbits at exactly the same rate as it turns on its axis. And to kind of drive home the point about the synchronous rotation, here's a nice GIF taken from the Wikipedia article on tidal locking, to which I certainly recommend you go, again, if you have trouble sleeping or you're just interested in learning more about this. You can see the difference between the sort of the moon's orbit around the Earth and in two cases, with synchronous rotation on the left and no rotation on the right. So if you look at the no rotation case first, you can see that the moon is obviously orbiting, and again, as basically everything in this lecture, these sketches or these diagrams are woefully not to scale. But you can see it's orbiting, but the relative orientation of the moon with respect to the page or to the screen is not changing. You can see the black shadowy parts of the moon are always to the left, and, you know, kind of the lighter gray side is always to the right. And so because the moon is not rotating about its axis, and that's just to clarify, when we say rotation here, we're talking about the moon's rotation about its axis. Obviously, the moon is orbiting. There's no question about that. So, but because on the right, the moon is not rotating about its axis, the side of the moon that faces the Earth changes throughout its orbit. Okay, sometimes one side of the Earth one side of the moon is facing the Earth, and sometimes the other is, and everywhere in between. In contrast, at left, where synchronous rotation is indicated, you see the moon is rotating about its axis at exactly the same rate, same number of degrees per night, as it is rotating about the Earth. And so the result is that, as sketched here, the dark side, you know, sort of the cratered parts, are always facing the Earth, and the lighter gray part is always facing away from the Earth. So in a nutshell, this is synchronous rotation. There's a lot of fun that can be had in trying to figure out, well, why on earth would the moon be in synchronous rotation? And there's a lot of fun you can have studying the gravitational effects that would lead to this. It has to do with the formation of the moon, and there are similar effects other places in the solar system, other moons that orbit other planets, and so on. And so that's why there's a Wikipedia article on it. and there's a lot of stuff written on it. So if you're interested in that, certainly there's more to be had. But this will do for us. Okay. So I mentioned eclipses a few slides back because, if you're not careful, you could be tempted into thinking that every time that the moon goes to the far side, kind of on the far side of the Earth from the sun, you end up with an eclipse of some sort. Moreover, there are people that will tell you that the reason that we have phases of the moon is because the Earth blocks some of the light, essentially saying that, well, phases are really just partial eclipses. And that is certainly not true. So it's tempting to say, but it's not true. So don't be fooled by that. But eclipses are a thing, both solar and lunar. And so let's spend a little bit of time talking about that now. So an eclipse in general can be either total or partial, but it's the obscuration. So just you're obscuring one celestial body by another one. Okay. And this is always going to have to do with the sun's light, right? The sun's light is going to be blocked either partially or completely by one body from another. So let's see what this actually looks like. And in particular, a solar eclipse then is going to be when the moon passes between the Earth and the sun, and so it's blocking the sun from getting to the Earth. So we call it a solar eclipse because from the Earth, we're looking up at the sun, we think, oh, it's a nice summer day, whatever, and then all of a sudden in the middle of the day, the sun starts going dark, okay, because it's being blocked by the moon. So everything, we call it a solar eclipse because the sun is getting blocked from our vantage point, right? And so, as you have probably heard over and over again, you should never look at a solar eclipse with your naked eye. And the reason is just that the visible light is largely blocked. Unless you have a very slight partial eclipse, if it's anything approximating, a total eclipse or even a significant partial eclipse, the brightness of the sun is significantly reduced. And so, under normal circumstances, if you go outside and you try to look up at the sun, you can only do it for a second, and then your body is smart, is designed well enough that it knows, to sort of close its eyes or avert them. You can't sort of keep them open even if you want to. Whereas during an eclipse, enough of the brightness is reduced that you can. The danger there is that while the visible light is reduced significantly, there is still enough ultraviolet light getting through that isn't bright because your eyes can't register that. They aren't made that way to handle ultraviolet light. But that light is even more energetic than the visible light, and it's still enough of it is still getting into your eyes that while you're looking up there thinking, wow, that looks really cool, your eyes being fried by the ultraviolet light. So that's the danger. So don't do it. There are safe ways to do it, and some of you may have followed those safe procedures and viewed solar eclipses in the past. But here are some pictures of a particular solar eclipse where you see that, here's the sun, and the moon is coming in. First, just a little bit is blocked, and then more and more. Finally, you have, in this particular case, we'll talk about it in more depth in a little bit, but we call this an annular eclipse because the moon is completely in front of the sun, but there's just a little ring of the sun that you can actually still see, and then the moon moves off, and the eclipse moves towards its completion. So this is what a solar eclipse, what a total solar eclipse would look like from Earth. In this, again, I mentioned this is called an annular eclipse in this case. Down here in the lower part of the slide, there's another set of images that is similar, but you can see the difference is that you don't have the annulus here. You don't have the annulus. What you do have, this is the corona. It's the atmosphere of the sun that normally you don't see. Normally if you look at the sun, it looks like it has a pretty clear edge. But in fact, there's a lot of interesting stuff in the sun's atmosphere. It does kind of extend a little ways. And we'll actually spend some time talking about that in a handful of weeks. But this is a different type of eclipse. Typically, this is just referred to as a total eclipse, whereas this first set of images up here is called an annular eclipse. And the difference just has to do with how far away the moon is from the Earth in its orbit. So I mentioned the moon's orbit around the Earth is very nearly circular, but it's not quite. Just like the Earth's orbit around the sun, it's slightly squashed. It is in ellipse. And so sometimes during the year, the moon is a little, or during the month, the moon is a little bit closer to the Earth, and sometimes it's just a little bit farther away. And then sometimes during the Earth, during the year, the Earth is a little bit closer to the sun, and sometimes it's a little bit farther away. And so when we're a little closer to the sun looks a little bit bigger in the sky, right? Not big enough that we would notice it day to day, but if you were a solar astronomer and you were taking very detailed measurements on how big the sun looked in the sky, this is a measurable effect. And so if the sun is a little bit bigger and the moon is a little bit farther away, is a little bit farther away, then it won't be able to block the entirety of the sun. And so that's what gives rise to an annular eclipse. In contrast, if the moon is a little bit closer to the Earth, then it will be a little bit bigger in the sky. It will appear a little bit larger to us, and so it will be able to block the sun a little more effectively. And so, incidentally, it is a complete accident, from a physics or astronomy point of view, that the sun and the moon are so very nearly the same apparent size in the sky, right? I mean, the sun is 93 million miles away. The moon is much, much closer. And much, much smaller. The fact that the moon is so much closer and so much smaller, and those two facts cancel each other out in the sense that they both look very similar sizes in the sky is really cool. And if it weren't the case, then we would not ever see total eclipses like this, right? But we do, and so we can be thankful. So here too, I gave you the sketches. These are kind of cooler because these are the real things. You see a total solar eclipse where you can see the extended corona and the sun's atmosphere, which you can see is quite large compared to what we actually typically see in the sky. You typically just can't make out, at least with the naked eye, you can't make out the sun's atmosphere just because while it looks bright here, it's certainly much less bright than the sun itself. And then here we have just one of the coolest pictures you'll ever see of an annular eclipse. With that's pretty phenomenal. So if you want to pause me here and just stare at that for a little while, I will understand. So I mentioned this just a little bit ago, but I'll give you 20 seconds or so to review and ponder it again. So when the moon's orbit, or when the moon is in its orbit and is slightly farther away from the Earth than it is on average, which of these two cases would we see? Would we tend to see a total solar eclipse on the left, or would we be more inclined to see an annular solar eclipse as on the right? And so again, I'll pause for a few seconds and let you think about that. So the way to remember this is just to imagine, well, what happens if the moon is farther away? As the moon moves farther away from the Earth, does it look bigger or smaller in the sky? And so, I hope that it's reasonably obvious that if you take the moon and you move it farther and farther away, it's going to look smaller and smaller and smaller, right? When we take, anything, it doesn't matter if it's an astronomical body or it's something, much nearer to home. As something moves farther away from you, it looks smaller, right? It's not really smaller, but it looks smaller in the sky. And so if the moon is farther away, it's going to look smaller in the sky, and that means it's going to block a little less of the sun's light, right? Because the sun is 93 million miles away, it just is. And so if the moon is a little bit farther away, it's going to block a little bit less of the sun, and so it won't be able to block all of the sun's light. and so you'll end up with an annular eclipse. And what you'll notice here, and so there you go, annular eclipse. What you'll notice is that in the annular eclipse, because you still see just a ring of the sun proper, if you will, you don't see the sun's atmosphere, right? You don't see the corona there. Whereas in the case of a total solar eclipse, where the moon is a little bit closer to Earth than its average distance, you actually block out the entirety of the sun proper. Now all of a sudden you're able to see this rather extended, pretty large region of extended atmosphere of the sun that is just not visible at any other time. And so I think that's pretty cool. Okay, so this is another sketch, kind of a schematic, again, very much not to scale, but gives you a sense of what's going on in the case of a solar eclipse. And so you've got the sun sitting out here, sending out light in every direction as it is wont to do. And then you've got the moon, which is in between the sun and the Earth. And so one important thing to notice from this sketch, and you may know this already just from from either following eclipses as they happen in real time or reading about them before or after. Even in the case that there's a total eclipse, that total eclipse is only visible in a relatively small part of the Earth, right? So anytime there's an eclipse, it'll be in the news. But any article worth reading will tell you where it's going to be visible, where it will be, if it's a total eclipse at all, where the total eclipse will be visible, and where partial eclipses will be visible. Because again, it's not, there's no such thing as an absolute total eclipse, where the light is blocked everywhere, right? The light, the sun may be completely blocked from certain places, but from other places, it will be either partially blocked or not blocked at all, right? It just depends. And so in this sketch, you can see that if you imagine a ray coming from the top of the sun, it comes down here, and if it skirts by the top, then it's not going to get blocked, and if it skirts by the bottom, it won't get blocked. So there's a region of total blockage, if you will, where no rays can get past the moon and land on this place on Earth. And so in that part of the Earth, in that region, you will see either a total or an annular eclipse, depending upon where the moon, how far the moon is from the Earth in its orbit at that time. But there's a much larger region of the Earth where there's a partial eclipse, where a lot of the sun's rays are blocked, but not all of them. So this is another interesting question to think about that I confess I'm not sure that I had ever thought about before I taught astronomy, but I think it's interesting, which is any time that we're going to have a solar eclipse, what phase does the moon have to be in? Okay, and I'll pause for a few seconds to let you ponder. Well, this is a pretty good sketch to work from, right? If we're going to have a solar eclipse, well, the moon has to be between the Earth and the sun, right? Well, what do we call that phase? Well, you can see here the side of the moon that's illuminated is facing the sun, obviously, as it always is, but it's facing directly away from the Earth, okay? So what phase is that? Well, that's a new moon, because none of the reflected light from the moon is heading towards the Earth. So, interesting thing. I'm kind of surprised, I said it was cool that, I found this out when I started teaching astronomy. I'm kind of surprised that this isn't mentioned, that somehow you don't grow up being told this in elementary school. But I guess, there's a lot to convey in elementary school, and so they can't tell you every interesting fact. But solar eclipses only happen during new moons. Okay, and there are a couple of other terms that we'll throw in here that, I'll be honest, we're not going to use a lot in this class going forward after this, at least after this module, certainly, because Our focus again this year in general, or this semester in general, is on stars in the universe. So not so much on things like eclipses, because those are decidedly inside the solar system. But you know, we have to cover it at least for a day or two. And so a couple of terms here associated with the shadow cast by the moon here. So the umbra is the region of space in which there is complete shadow. Okay, so it's the part where the moon is blocking all of the sun's rays. So you can see, and it's completely dark, completely black here. And if you were on the Earth and in the umbra, then you're experiencing a total eclipse. Okay, that's what a total eclipse is when the umbra of the moon passes over some region of the Earth. Okay, but there's a much larger shadow, partial shadow, called the penumbra, in which you can see some, possibly a lot of, but not all of the sun's rays are being blocked. And so if the Earth, or if the region of Earth in which you happen to reside happens to pass through the moon's penumbra, then you experience a partial eclipse. And solar eclipses happen with some frequency. Every year there are some. How many varies somewhat. And where those are visible varies a lot. And so you can see, I throw this up here. This is the kind of thing that you will never be asked to regurgitate or remember. But it just kind of goes to show you where total eclipses in yellow and partial eclipses in red are visible. And you can see they're all over the map, literally. So, you know, there are more partial eclipses than total eclipses, which probably isn't a surprise. It's easier to block part of the sun than all of the sun. And then certainly there are ones that are, you know, down here in the very south, you know, or I guess in the Antarctic Sea, if you will, that not a lot of people are going to see this one. You know, and similarly, there are some up in the far northern reaches that maybe there are a few polar bears that'll see, but not many others. But then there's just a lot of variation as far as, you know, where these things show up. I can't call it random because it's not random. We can calculate it with a lot of certainty now, but it varies a lot. And so, and people do calculate it though. So if you're interested, you can go Google, you know, solar eclipses for the next decade, and there are websites dedicated to that'll tell you exactly where these things are going to be. I have not been to one specifically that can just, you know, you can give it your city and say, tell me when the next, you know, 17 solar eclipses are going to occur here. But I would almost bet that such things exist. So usually we see a solar eclipse, you know, every handful of years, you know, at any given location. Usually it's a partial rather than a complete solar eclipse. And obviously whether you can actually see it or not depends upon weather too. You know, I grew up in Indiana, and in Indiana, you know, we have a lot of clouds and thunderstorms, especially in the summer and things like that. Weather is actually a thing, unlike, you know, out here in California where, you know, smoke and wildfires are things. But we don't get a lot of thunderstorms and cloud cover most of the year anyway. So anyway, you can, there's a whole lot that you could study about eclipses, but this will be good enough for us for now. Okay. So we've talked about a solar eclipse. Let's now talk about a lunar eclipse. And as you probably gathered, if a solar eclipse means the sun is being blocked, well, a lunar eclipse means the moon is being blocked. So in other words, you can imagine you're out at night, you know, enjoying the evening and watching the moon, and then all of a sudden the moon starts to disappear. And you think, why on earth is it disappearing? Well, let's think first about why it was ever visible to begin with, right? So the moon is visible. It doesn't generate its own light, right? It's not a star. The moon is only visible because it's reflecting light from the sun. So if the Earth manages to block that light from getting to the moon, then you're not going to see it anymore. Okay, and so that's exactly what happens. So just like the moon can cast a shadow consisting of an umbra and a penumbra, the Earth can also cast a shadow. And as it turns out, the Earth casts a much larger shadow because it's quite a bit larger than the moon. And so again, in this horribly not to scale sketch here, you have the sun casting its rays towards the Earth and the moon, and the Earth blocks the moon then, and so you see the Earth's umbra is pretty big because relative to the moon, because the Earth is pretty big relative to the moon. So you've got this big shadow. You also do have penumbra, so that's still a thing. But the moon now, if it's back here in this, on the other side, it's getting completely blocked now, and so it's going to disappear. And so that will be a lunar eclipse. So as you can imagine, total lunar eclipses are more common than total solar eclipses, just because the Earth's shadow is much larger relative to the moon than the moon's shadow is relative to the Earth. So let's ask this question now. Why isn't every new moon a solar eclipse, right? So you've seen this image before. Here we're at a new moon. Why isn't this always a solar eclipse? Okay. And similarly, why isn't every full moon over here a lunar eclipse? Okay, because, and we kind of touched on this earlier, but it sure looks like from this sketch, if I'm sitting here at a new moon, well, the moon is in between the sun and the Earth, so isn't it blocking that light completely? And isn't that a solar eclipse then? And similarly, the full moon, it sure looks like the Earth is in between the sun and the moon. So I've drawn, I have this bright side of the moon, but how on earth is that getting lit up? Because isn't the Earth blocking that light? Okay. And so I actually addressed this quite a while ago, but I really think this is important to drive home, because I have to say, I knew, I remember this being discussed in 8th grade, for what it's worth. I knew that this was not the case, that every new moon was not a solar eclipse and every full moon was not a lunar eclipse. I knew the phases of the moon were different than eclipses, but it was always really confusing in my mind as to why that was. Okay, and the answer is what I mentioned earlier, and here you actually have a nice diagram, so I think this will help solidify or maybe make some sense at all out of what I said earlier. And the point is that the plane of the moon's orbit is different than, by a little bit, it's tilted a little bit relative to the plane of the solar system, the plane of the Earth's orbit. And that angle, if you're precise and you like numbers, that angle is 5.2 degrees. And so what it means is that the moon, as it orbits, it passes through twice in every orbit, it passes through this plane. But most of the time, it's either above the Earth and the sun's plane or below the Earth and the sun's plane. Okay, and so if it's above the plane or below the plane, unless it's very close to the plane, it's not going to cause an eclipse at all, right? Because it's just the sun will be able to get to the moon, and it will be able to reflect back to the Earth, because the Earth can't block effectively when the moon is not in that plane. So the only time that eclipses can happen is when the moon happens, is at or very near one of these 2 points, when the moon passes through this plane of the Earth's orbit around the sun. And so you can see, I think this, again, I like this diagram because it's got some things labeled here that are helpful. You can see that they call this or label this a missed solar eclipse, in the sense that, well, the moon is in between the Earth and the sun, and so you would be inclined, if you didn't look at it from this vantage point, you would say, aha, the moon is right in between the Earth and the sun. It's going to block that light. It's going to be a solar eclipse. But alas, the moon is outside the plane. It's below the sort of the orbital plane of the Earth and the sun. And so as a result, the sunlight has no problem flying just over the moon and making its way to Earth. And so, and that happens far more than it doesn't, right? There are a lot more missed eclipses than there are actual eclipses, which is part of the reason why eclipses are more exciting than phases of the moon. Okay, so anyway, that's where we're going to stop today, and that is all that we're going to say about eclipses and the like. So thanks for sticking with me, and I will see you back here next time for Lecture 5.